Hello everyone, I'm Han Chen, currently a master student at Tongji University, and I was a research intern at Alibaba Damo Academy. Here I'm very glad to present our work EPro-PnP, Generalized End-to-End Probabilistic Perspective Endpoints for Monocular Object Pose Estimation. In this paper, we investigate a long-standing problem in computer vision that is locating 3D objects from a single RGB image. Given an image containing the projection of a 3D object, our goal is to find the rigid body transformation from the object frame to the camera frame. This is called the object pose, denoted by Y, and it can be decomposed into the orientation component and the position component. To solve this problem, a major category of methods is direct pose prediction, or the explicit method, which is very popular in 3D object detection. Typically, we build a feed-forward network that predicts the 2D location, the depth, and the orientation of the object. So with annotated training data, a loss function can be designed to directly supervise the object pose. So this method benefits a lot from a simple end-to-end training pipeline, but the problem is it lacks interpretability and may be prone to overfitting. Another category is going implicit, that is geometry-based pose estimation, which is very popular in 6DOF pose estimation tasks where object shapes are known a priori. Here we focus on the most common method, the perspective endpoint or PnP method. In this method, we first need to find endpoints in both the image and the object frame, with 3D coordinates x3d, 2D coordinates x2d, and optionally the corresponding weights w2d. From these endpoints, the object pose is implicitly defined as the solution to an optimization problem. That means we can find the optimal pose that complies with the projection rules, where every projected 3D point shall coincide with the corresponding 2D point in the image. Formally, the PnP solver minimizes the cumulative square-weighted reprojection error, where the error of each point is a function f of the object pose y. Today, PnP methods are often combined with deep learning. The common inference pipeline is to deploy a feed-forward network to predict the 2D-3D correspondence set X, and then solve the object pose via a PnP solver. This combined model has much better interpretability and stable generalization performance, but the training methods in prior work are rather limited. Most of the methods rely heavily on a surrogate loss that supervises these intermediate variables, which is not optimal for best pose accuracy. For example, some defines a couple of 3D key points in the object frame, so the goal is to find the 2D key points in the image. Another example is dense correspondence, where every pixel of the image is taken as a 2D point, so we need to predict the dense 3D coordinates and the segmentation mask. However, none of these methods are flexible enough since only a part of the variables are learned. What if we don't know the object shape at all, and all these intermediate variables have to be learned from scratch? And that brings our attention to the end-to-end pose loss, which backpropagates through the optimization layer via implicit differentiation. The training is still very unstable since argmin function is generally non-differentiable. Here is an illustration of this issue. A change in the correspondence x will cause a change of the cost function, hence a change of the optimal pose y star. But sometimes the change is discontinuous as the global optimum jumps from one mode to another. So, to achieve stable end-to-end training, we introduce the end-to-end probabilistic perspective endpoint layer. The idea is to interpret the pose as a probability distribution, whose probability density is always differentiable. We first define a likelihood function based on the cumulative reprojection error, and with uninformative prior, normalizing the likelihood yields the posterior probability density. This formulation can also be regarded as a continuous counterpart of the categorical softmax function, which is widely used in classification problems. So essentially, EPro-PnP replaces the regular argument function with a differentiable soft argument. During training, given the ground truth pose, we can define a target pose distribution and minimize decay divergence between the target and the prediction. Again, this is analogous to the categorical cross-entropy loss, but on a continuous domain. With the K divergence loss, we make sure that all potential pose solutions contribute to the loss function, which guarantees global convergence. As of the target distribution, we use Dirac delta distribution whose variance approaches zero, which yields the simplified loss function. Taking the gradients, and we can see that it tries to minimize the reprojection error at target pose while maximizing the reprojection error over the predicted pose. Now, because we're using weighted correspondences, these two terms drive the weights to be both uncertainty aware and discriminative. Being uncertainty aware indicates the inner region with higher confidence shall be weighted more, and being discriminative means the point sensitive to the variation of pose shall be weighted more. This balance helps the model to focus on the important regions in the image, somehow resembling the attention mechanism. Therefore, we no longer need to cherry-pick the key points or use segmentation mask. Now, the only problem is the pose distribution is intractable and has to be approximated numerically. A simple approach is Laplace approximation. This requires solving the optimal pose, computing the local covariance matrix, and using the normal distribution as an approximation. However, this is effectively a generalization of the implicit differentiation method because we're still backpropagating through the optimal pose y star, and it can be seen that normal distribution fails to capture other modes, so it is still inaccurate. Therefore, we resort to Monte Carlo methods and adopt the adaptive multiple importance sampling algorithm to draw weighted samples from the distribution so that the second term of the decay loss is approximated by the importance weights. Now, to find out whether EPro-PnP layer can improve existing PnP-based networks, we test a 6DOF pose estimation network based on CDPN, which is a dense correspondence method. We remove its translation head because it's based on depth regression and keeps only the coordinate branch that predicts dense 3D coordinates and weights via CNN. And we add some minor modifications to the last layer. The experiments show that simply adding the basic EPro-PnP loss during training significantly improves the pose accuracy, and with some training tricks, it is able to compete against the state-of-the-art. Compared to other methods, EPro-PnP retains a simple and elegant architecture based solely on the PnP solver. No explicit depth prediction, no pose refiner, and this makes our method very fast compared to some more complicated methods. Furthermore, we explore the flexibility of EPro-PnP by proposing a novel deformable correspondence network for 3D object detection, which frees the points from a fixed pattern. In this network, the entire 3D, 2D coordinates and weights are learned from scratch. More specifically, we use FCOS 3D as a base detector to generate object queries, which are fed into the deformable sampling layer inspired by deformable DETR. To generate 2D 3D correspondences, we first predict the locations of the 2D points and then extract the point-wise features by interpolating a dense feature map, and finally adopt a very small point transformer to predict the 3D coordinates and weights of each point. Another object-level branch is responsible for dealing with some extra predictions such as the confidence score and the size of the 3D bounding box. The resulting network not only surpasses the FCOS 3D baseline, but also outperforms the state-of-the-art at the time of submission. It should be noted that none of these competitors have tried the PnP method before, since end-to-end training is very important on such a large dataset. Therefore, it can be concluded that EPro-PnP combines the best of both the implicit and the explicit methods. Here are some visualizations. If you use Monte Carlo PnP at test time, you can even draw the probability density of object position, which reflects the localization uncertainty. Another very important advantage of EPro-PnP is that it naturally handles the ambiguous orientation case by predicting the multimodal distribution, which occurs under symmetricity or uncertain observations. For future work, it is promising to apply EPro-PnP to other PnP-based post-estimation networks, including self-camera localization, or we can design novel networks that leverages its flexibility. For example, the geometry constraints do not have to be limited to point relationships. And beyond post-estimation, we hope it can be generalized to other learning models with nested optimization layers. Thank you very much for watching this video. If you want to try EPro-PnP, you can visit our GitHub repo.